Hi all, I'm Varsha and I'm here with Aiden and Christian. We are Group 54 and we are here to present an update on our project on brain tumor classification using a CNN. Brain tumors pose a significant threat to human health, requiring timely and accurate diagnosis for effective treatment. Magnetic resonance imaging (MRI) is a crucial tool for visualizing brain structures and detecting abnormalities like tumors. However, manual interpretation of MRI scans is a time consuming and subjective process, prone to inter observer variability and potential for misdiagnosis, especially in resource constrained environments or with increasing patient loads. This project aims to address this challenge by developing a robust and efficient neural network based system that can automate the detection of brain tumors within MRI images and classify the detected tumors into the following categories that are glioma, meningioma, and pituitary. The data set used in this project is the brain tumor MRI dataset available on Kaggle. It contains 7,023 MRI images labeled into four categories, that is glioma, meningioma, pituitary, and no tumor. While it's not labeled, the dataset also includes three kinds of MRI scans that are axial, sagittal, and coronal. Once the model is deployed, it will accept images of MRI scans as the input and generate a text output that classifies the tumor as glioma, meningioma, pituitary, or no tumor.
So for our baseline model, we decided to use some transfer learning with the exception and Adamax optimizer. Our motivation for using these two baseline models was from two papers that we studied that showed that exception was an excellent computer vision model for especially medical related visual detection problems, and the Adamax optimizer was excellent for reducing loss in these cases. So for our baseline, we modeled the architectures as follows. It was an exception model as seen in this diagram to perform the convolution, flatten layer to transform the output of the exception model into 1D vectors, and a fully connected layer to reduce the output to 4. And that was for our baseline. Since then, we decided to add some additional dense and normalization and dropout layers in an attempt to increase our accuracy. And the result was that across the layers, uh, the variance increased, but the bias had decreased. And what this ultimately resulted in was some overfitting, and our performance actually dropped. So instead, we decided to stick with the baseline exception model and a dense layer, and then implemented a callback function to obtain the model from the epoch with the best validation loss. And this addressed the overfitting and gave us the best accuracy we had seen.
And so handling this bias and variance trade-off, we were able to increase our accuracy from originally with the baseline model 99.4% all the way up to 99.8% on the test set, 99.85% on the test set. It so happened that during this training run, the best epic was epic 10, and so the model was saved at the end of Epic 9, and then we were able to save that model and run the model on our test set. And here are our performance metrics rounded to the second decimal place. And we were also able to solve the problem where in a high critical situation, we would not want to classify a tumor as perhaps a no tumor. So we did not want a false negative there where something that actually was a tumor was classified as a no tumor. That would be bad. We were able to get rid of that from our original baseline. And we were able to see that our single misclassification occurs on a meningioma that was predicted as a glioma. So we were able to at least show that our predictions were not misclassified as cancer or non-cancer, just a different type of cancer. And we do have some prior work in neural network architectures. And here are references, and thank you very much.